So, hello everyone. Good morning. I'm Alex Miller. I work for Cognitect and work on Clojure itself. I'm one of the core team, work on the implementing new features and working on tickets and stuff like that. My sort of personal background is really the bulk of my software career was spent doing Java, a lot of Java. So this talk is in some ways my nth attempt to sort of explain to people why I like Clojure so much, having come from Java. And to do that, I'm going to talk about a bunch of Java stuff. How many people here are familiar with Java? Is it most people? Okay. How many people have done like at least a little bit of Clojure? Say. How many people have done a lot of Clojure? A few. Okay. So that's good. That's a good mix. I'm going to talk about a bunch of Java stuff, but have no fear, we'll get to Clojure down the line. So the problem that I'm going to sort of work from and come back to throughout this talk is for each repo in a GitHub organization, who made the most commits. So if we go to, for example, the Clojure organization, there's the Clojure itself, there's a bunch of other repos. Who made the most commits in each of those organizations? So this problem is not in any way interesting. It's just something to give us a touch point to start talking about these things. And I think it's enough to bring up all of the problems that made me frustrated with using Java over a decade plus, and the reason that I find Clojure so refreshing. So we're going to talk about things like domain data and transforming data and things like that. So sort of some pseudocode for what we're doing here. We're going to initialize sort of a map of repository to the user that made the most commits. For each repo in the organization, we're going to initialize those counts. For each commit in the repo, we're going to increment our counter. And then when we get to the end, we're going to record the user that had the most commits and return the final map. So this is just some simple code here. Some of the things we're going to talk about are data representation, sort of how we represent our domain objects, encapsulation, how we're sort of holding our data, means of abstraction, how we manage state, how we transform data from one form to another, and eventually we'll get to talking about things, some functional programming type things. I'm going to go through a little bit of code here. There's actually 3 slides of code I'm going to talk through. And this is it's definitely not the only way you could do this in Java. It's definitely, now that we have streams, it's definitely not the only way you can do it. I do have a stream implementation that we can look at the end of the talk if there's time to do that. But I'm really trying to represent the way that sort of most typical Java code is written or has been written for a long time. And like I said, this is not designed to be perfect code. It really doesn't matter. It's just enough to get us talking about things. I'm using this eGit GitHub library. I think others exist. It was the first one that I found, and so I used it. It seems to be it did everything I asked it to do, so I was happy with that from a Java perspective, and I saw a lot of things in it that seemed to be very typical Java idioms and things like that. So what we're going to do here is this method, most commits per repo. We need to get some things from the library to be able to talk to the GitHub API. We're going to initialize our map. This is sort of the return value that we're going to return at the end. We're going to walk through every repository. And so here we call repo service.get repositories. That's going to return to us a list of repositories, which is a typical Java thing to do. We're then using this repository repo, we're walking through it element by element. And so this kind of replaced the old style for loops where you're iterating through, where you would explicitly get an iterator and then walk through the iterator next. And so that was a change that happened in Java 5, and that was a very welcome addition. I was tired of writing iterator all over and over again. And so now instead we do this. And so it's this sort of element by element approach to working with data. And at the end, or the last line here, we're going to initialize a collection that we're going to use per repository just to track the number of commits that we have. So next chunk of code, here we're basically walking through, we're going to call the commit service and get a list of commits for the repository. And so it gets every git commit in the repository. And so this takes a while, actually, if you run this. It doesn't take a long time, but it takes a little while. And there is a rate limit on the GitHub API, if anybody is interested, which is 5,000 calls per hour. So I blew that once in testing this out. Again, we're going to see the exact same kind of code. We're going to walk through with a for loop, this iterator of walking through every commit in a list of commits. And then there's a little bit of code here that's sort of trying to come up with a good name for the author. I probably should have extracted this out, and I actually did in the stream version. But here it's in line. Basically, if the committer is a GitHub user, then you'll get back a GitHub user here. The author will be a user object that actually is the GitHub user. But because GitHub is just wrapping just general Git, there can be commits in your repository that didn't come from an actual GitHub user.
That's going to explode.
What's that?
That's going to explode because you have the conditional there where author equals null, and then you call author.getLogin to a failure case, which is going to result in a null pointer exception.
No, it's in the else case.
Yeah, it's going to result in a null pointer exception. Yeah.
No, but if it's null, if it is null, then we'll use the commit.getCommit line. So it's in the else. Yeah, that's what we're protecting against there. And so what I'm doing is instead of getting the user, I'll just go look up the actual author that the commit listed here. And then I'm using a method that was added in Java 8, this compute method that lets you actually say, in this map for the key here, login, apply this function to the value and replace the value with that with the new value you create. And this is what you would have done before Java 8 is to get the value out, compute a new value, and then put it back into the map. So this has allowed me to tidy up that little part of the code a little bit. It's basically saying if the author's already in there, then increment the count, but if not, then just put 1 in. So we're seeing lots of these domain objects as we go through. We see user, we see repository commit, we see repository was another one. We see this style of iterating sort of element by element through a list of things. So those are some things I wanted to point out. Oh, and then there's another chunk of code here to sort of walk through, once I've built up this map of the counts, to walk through and find the highest count. There's other ways you could do this. I could have put it in a tree, in a sorted map and pulled the last one out of that or something like that. Again, it's not really that important. So this is, again, just more of the same kind of code. And so a lot of Java code looks like this. So if we go back to the actual GitHub API and the actual web service involved here, you'll see that all those Java objects that we've got, all those repository and commit and all those things, are really coming back from the GitHub server as JSON objects. And so this is what they actually look like coming from the server. You've got these maps of attributes and values. And in some cases, they're nested. So here, like that owner that's in here for the repository is nested inside the repository. And there's lots more. I've omitted it, but there's dozens of attributes, right? And so the Java API very idiomatically wraps each of these sort of domain types into a Java object. So this is the repository object. It's got a whole bunch of getters. It's also got some setters and typical stuff like that, right? And so this is the typical plain old Java object that you see everywhere. That's how most data in Java is sort of passed around and how people model data in Java. Just and have for a long time. And obviously, like, this conforms to the Java Beans spec, and there's all sorts of tools that know to sort of reflectively understand these kinds of objects. So a question some people ask is, why do we have getters and setters instead of just calling these fields directly? Does anybody have anything? Yeah.
Because the interface to it is private by default.
So you're encapsulating the fields and making it private. That's one good reason. Is there anybody have any other ideas, thoughts? No?
That's the way it's by default.
Because that's just the way it is, right? Yeah? So the getter could do additional logic, right? That's another case.
I think it's mainly because these getters and setters that we can have an interface where otherwise you can't direct.
That's another one. So it allows you to create interfaces and things like that. So these are some of the reasons. But sort of another thing is that if you have a getter, it gives you, like if you were going to use fields for some things, but later on, like if you wanted to do direct field access, and then later on you decided, oh, I do need some custom logic, right? You're going to break all your users of your object if you switch to using a getter. So there's no sort of consistent syntax for getting from fields to getters. So people just say, well, in case I ever need it, I'm just going to make a getter. So, there's a lot of different reasons here. I think when I step back and really think about this, though, I think about these as sort of data interfaces. Like these objects, they don't, like most of these objects, when you create them, they're just fields and getters and setters. Like it's not entirely, I mean, that's not always true, but there's a large number of them out there, I'd say, that are really sort of wrapping the data in this class, which is the interface to your data. And to use that interface, we need to have one and know what those methods are. And so the way I think when I go back and write Java now, like the way I think about it is like I'm typing this get name, get age, get whatever, and I'm thinking like nobody knows how to call these methods. Like these, I'm creating an API here. If it's a very small API, just wrapped around one little domain object, but I'm really creating a whole new API that no one knows how to use. And so I think about those domain objects now as being just like, as having this sort of custom data interface. And it's actually like really problematic. It generates an entire, like huge amounts of code that's noise. There's boilerplate noise, and it really bothers me now coming back from Clojure. But we'll talk about what Clojure does instead. So another thing that we care about is, say that we have, like this exists in the API for this GitHub client in many places. So you'll see two domain objects that have the same method in them. And so that's because they have the same attribute that's coming back from the server. So one thing you'll see is get HTML URL. So a repository object has a URL that points to the repository. A user has one, an organization has one. There's a bunch of different domain objects that map to a URL of some kind. Those things don't, like, if I had a collection of things a heterogeneous collection of like repositories and users, there's no way for me to sort of generically call into that. I can't call that method. There's no abstraction there, even though there really is like a commonality there. There's a common data attribute, and you have the identical interface in two different classes, but you can't get to it. That's really frustrating. And so you can't really solve this without some sort of reflective or metaprogramming type tool.
Anytime you're going to have a heterogeneous collection, maybe you should just slap an interface on to guys like HTML URL provider, field layer. Yeah.
Right, and so.
Yeah, but his point was that without having done that ahead of time, you can't add that after the fact.
Right. And so if you want to do this, you're going to have to create an interface, right? And that you're going to have to then change your two classes or n classes that implement that method to also implement that, to implement that interface. And so that's problematic. I think we already mentioned a few of those things. One reason that's really subtle that it took me a while to realize is that this works. I mean, you can totally like create an interface and extend your classes and all that stuff. But think about what you just did. You just made more code. Like, you made things more abstract. Like, you created a new abstraction that didn't exist, and it allowed you to use things. But you actually, in the process of doing it, you actually made your code base larger. And so I've worked on, Java code bases that were hundreds of thousands of lines of code. And in the long term, this is not a good trend. So you want tools for abstraction that let you make your code shorter. That's how you win. That's the only way to fight complexity is over time is to have things that let you create abstractions that really let you exploit that commonality with less work instead of more work. So that's something. Another thing is that we have to actually modify those existing classes. And so, Java classes, they're sort of closed without, you have to go in and actually add the interface to those classes. And in this case, like maybe we had control of those interfaces, but like if I'm using this GitHub library, like I don't have control over their domain objects. I can't go in and do this after the fact. There's no path for me to do that. There are some new things you can do with default methods and things like that, but they're not really, I don't think they're solving this problem in any sort of a good way. So that's a problem. We've really limited our ability to abstract over data. Another thing that doesn't exist is sort of good tools for deep inspection and retrieval. So when we have sort of nested trees of domain objects, say I have that get HTML URL method, how do I like walk up to a big tree of those things, a big sort of tree of domain objects, and say, give me all the URLs? I can certainly write some code, some recursive code that handles every possible type in some sort of a switch or if else or something like that, and build custom navigation that iterates through all of those things. And there are techniques like visitors, and I've built domain objects with visitor pattern stuff, and that all works. It totally works. But if you've used the visitor pattern, like it litters this boilerplate junk all over every class in your domain objects. It's totally non-reusable. When you pick it up and walk to the next project with a new set of domain objects, you've got the exact same problem, and you have to start over and basically re-implement all the same boilerplate all over again. And you have to sort of plan for that in advance. You really want something that lets you do sort of like XPath or something, like something is describe what's down inside my data. And you don't have any of these generic access mechanisms that let you build that. Just sort of summing up where we are so far, encapsulation of fields has some cost to it. It has this sort of increase in code size. It has problems with lack of abstraction or tools for abstraction. If we want to get some sort of generic use of our data, we require creating new abstractions with interfaces. We're going to have to change existing classes to do that. We don't have tools for generic navigation retrieval, but if you build them, you still have this increase in code size and complexity. And we haven't talked about state and concurrency yet. So this is where things can get really bad. So if we've got multiple threads that have access to these POJOs, then what do we do, right? And I'm not going to belabor this too much, but because I think it's been well discussed. But you need some way to some model for how you expect these domain objects to be used. You need to control that data in some way so it can be used safely. And there's a bunch of different ways to do this. I mean, one path is that a lot of Java code takes is just to assume that you're only going to have single-threaded or single-owner access to a particular instance of a domain object. And in that case, either I'm just using it in one thread and I'll end up being done with it, or I will transfer it to another thread over some concurrent collection that will do all the necessary locking for me to do that safely, to do that transfer safely. And that's a really solid strategy, and a lot of Java code, I think, falls into that bucket. If you do actually need concurrent access to a domain object, then you're into dealing with locking and synchronization protocols, really. You really are then creating a concurrency protocol for your domain object. There are lots of choices in how you do that. You can do it on a per class basis, a per field, per groups of field. All of those things have, you have to make a choice about how to do all of those things. You have to, some of them require your users to lock externally or do something. In some cases, external users might need to know what that protocol is. There are performance trade-offs for a lot of these things. So that's an issue. Another technique, which I don't have on here, is sort of cloning or copying, so that you never, anytime you're giving data to somebody else, you copy that data. That obviously, again, has performance characteristics that are not great. Immutability is a really good option. We'll talk about that later. One thing I found as I was just looking through these domain objects in this GitHub library, and I'm really not picking on this library, it's a good library. But one thing that I saw when I went through here is that one of the setters in the repository, and this is not true of all the setters, but this particular one, you're passing in a new date object for this repository. So when I see this, I immediately think, oh, this is whoever wrote this code is trying to protect themselves. They're being passed a mutable object from somewhere else that they don't know anything about, right? They don't know where it came from. They don't know who else is going to modify it at some point down the line. So I'm not going to keep a reference to that object myself. I'm going to clone that object and create a new copy of it to keep it around. And the really crazy thing here is that date is a long, right? It's a value. So the fact that date is mutable is just that's been well discussed, but that's not a good thing. And this is and note that this doesn't even actually solve the problem. Like if in between the point when set updated at starts and the clone is called, somebody could have modified that object already, right? If this is really a problem, you haven't actually solved it. Their caller has to do that. And what if the caller actually is just created this date, is not going to do anything with it, which is probably 99% of the time. This is probably not even an issue. And so I've actually introduced a copy here when I didn't. I'm creating a new object and copying a new value into it. So I'm creating garbage, and that's I'm sort of defensively trying to protect myself from problems that are probably not actually problems. So I've created more performance issues. This is just really common kind of stuff you see in Java. So more problems. Mutable shared state has all these costs associated with it. Mutable objects can be really fast, right? You can do really fast things with them if you're mutating them in place. The problem is that it's not safe to do that in general. We're gaining this performance benefit, but taking on this giant cost of complexity and decisions about concurrency models and all this stuff. And a lot of opportunities for error. I mean, there's so many ways this can go badly wrong. And so I would contend that's a problem. We've also talked about iterator traversal in that Java code. Java objects are held in collections. The iterators are the most common way that we sort of walk through them and traverse them. Iterators are terrible. They just really are bad. They're stateful. You can't reuse. If you get one and you pass it to somebody else, then you've got two things that are trying to contend for the same stateful thing. You can't copy it and fork them in any way. You can't I'll give you a copy of the iterator and I'll keep one and we'll do different. You can't do that. And they're sensitive to changes in the underlying data. If you have a collection, you rip an iterator off it, you give it to somebody, and then what happens when you change the collection? And the answer is, it depends, right? It depends a lot on what kind of collection it is and what you're doing to it, and there's answers for all those questions, but they're messy. There's lots and lots of messy stuff there. So more problems. So people probably saw Brian's talk yesterday about streams. I didn't actually see it myself, but I imagine in my head what it was like. And it does definitely address some of the problems of iterators. I mean, some of these things with statefulness and so just some of the pain of sort of transforming and manipulating data. It definitely helps. And I haven't really, because I've been using Clojure for a number of years, I haven't really used Java 8 much. But I kind of worked on it a bit for this presentation, and there's a lot of nice stuff there. There's a lot of it's better. So If I was still using Java, I'd be happy about it. But it doesn't quite go anywhere near far enough, and it doesn't help at all with the domain object issues or things like that. And I'm really not picking on Java because I still have a great fondness for Java. It fed me for a long time, and still does, secondarily. And I have the utmost respect for Brian Getz and all the Java team. They do amazing stuff. So I'm very thankful for everything we've gotten. But we can come back and look at streams at the end. So let's switch gears, talk about Clojure a little bit. This is not at all a sort of intro to Clojure. I'm going to talk about a few things, and hopefully most people have seen enough Clojure that it will make sense. But if it doesn't, feel free to raise your hand, and I'm happy to be interrupted. And that would be better than just walking by and having no clue what we're talking about. So that's fine. So in Clojure, this is a big chunk of the model. I tried to fit it on one slide. All data is immutable. So simple values, things like strings and numbers and booleans and stuff like that, those are immutable, which is true of Java as well. The important part here is that collections are also immutable. So that means when I create composite values, those composites are also immutable. And I can, if I modify one, and I'll say modify just because it's tedious to say anything else, but what I mean is, change it and give me back a new version. And the old version still continues to exist and be immutable and all that. We have generic data interfaces. We have just a small number of core collections. We have built-in support for generic attributes. We have lots of tools for generically manipulating data, sort of without having to a priori know all of the interfaces and things like that. It's really it's really huge. I can't emphasize enough how much that changes the way that you deal with data and think about data. And we have the sequence model, which I'm going to talk about each of these a little bit more in depth, but we have the sequence model, which is sort of a generic abstraction for traversing sequential data. And all of they're sort of immutable views, and you can use them like collections because they're immutable. So that sort of blurring the line between this abstraction of sequential access and actual concrete data is really subtle, but it's something that is sort of pervasive throughout the Clojure design. The fact that you can do that is really, really powerful. You can, take this collection and then create a sequence from it and manipulate the sequence, then pass it into something else. And most of the time, that thing that's getting it doesn't care whether it got an actual collection or whether it got a sequence. And blurring, that blurring is really, really important. We have stateful constructs. So instead of having all these different, needing to define sort of this concurrency model around every domain object, we've got these immutable values. And then if we need state, we can explicitly create that with an identity. And then, so we separate the identity from the actual values it's holding. That's important. All right, so a little remedial Clojure. There's 4 basic collection types in Clojure: lists, vectors, sets, and maps. So lists use and these are literal collection syntax. I didn't mention that in the Java part, but I mean, Java doesn't really have a literal syntax for collections, and there's tools now to do some of that stuff, like the of methods and things like that. But having literal syntax for lists and vectors and sets and maps in particular is really, really useful. I wanted to mention, so all of the collections are immutable. All of the collections are also persistent. And so by persistent, we don't mean storage. We mean basically that as we build a new sort of modified collection, if we add an element to a vector, you're going to reuse as much of the old vector as you can in building the new vector. And that's safe to do because it's immutable, right? We can, if we add a new element to the end, we can basically have most of the old data structure that's out there, and then you've created something around that that's going to use the old data but also append the new data. And then there's a lot of stuff inside the implementation of those to make that efficient. And it's not as efficient as mutable as modifying mutable objects. But it's efficient enough for the stuff you do with it. And the benefits are vast. So that's a trade-off we're willing to make. And there are, everything I'm telling you is lies. So there are exceptions and caveats and other things you can do, in almost every case of what I'm telling you. But I'm going to tell you the sort of the main thread story. So there are lots of options for things. Anytime you compare collections, they're compared by value, not by identity. So when creating an equals object in Java, I didn't even go into all that stuff, the equals and hash code and all that stuff. But you really, in Java objects, you typically need to define sort of the equality semantics for every object. So you identify some key, and your equals method is going to check that series of whatever fields constitute the key for the domain objects, or there's a bunch of different strategies there, right? Whereas in Java and in Clojure, there's just one strategy, which is they're compared by value. So if you've got a list, if you've got two vectors, you're going to say, are they both vectors? Are we going to walk through each of those things? And is it the same set of elements in the same order? Also, every collection is heterogeneous, so you can put any type of thing in there. You can put numbers and strings and whatever and mix them all up. And everything nests, so you can put any kind of collection in any other kind of collection. So that gives you enough. That's definitely enough. I mean, we have more here than you have in JSON, right? And I think we've proved we can put anything in JSON at this point. Yeah.
So when you mentioned equality, and you say it's the same value,
Mm-hmm.
what do you mean by that?
So yeah, it's a good question. So the question is, what do you mean by same value? And so you have to sort of build up from the bottom, right? So you've got a bunch of different primitive value types, right? Which are similar to Java's but not identical. So things like longs and doubles and big integers and big decimals and strings and characters and booleans and all those things, right? And then the question is like, what happens when you start to combine those things? And so that's where we define it. We say, a vector is you're sort of recursively defining this equality concept up from that. I don't really have any slides on this, but collections are actually break into 3 different equality partitions. So there's maps, and maps are equal if they have the same keys, and every key maps to the same value, so the values compare as equal. Sets are equal if basically every element appears exactly in the 2 sets you're comparing. And then the third equality partition is really sequential data. And so lists and vectors are actually compared the same. So, and sequences. So all 3 of those and any other sequential data are basically, do you have the same elements in the same order? And so that's how they're compared.
Like for strings, for example.
Right.
Are you doing like character comparisons for actual quality?
So
even if they're immutable, they're not necessarily the same.
Right, yeah, you're going to use a dot equals kind of call on a string. So it's not an identity call in general anywhere. Basically, if it's not something that Clojure is defining, then it's going to fall through to the Java dot equals method in most cases. Yeah. There's a few differences there with things like booleans. Clojure does establish a canonical boolean value, which is the boolean dot false or whatever. And so there can be some issues around that, things like that. And then there are actually additional notions of numeric equality, and so there is support for things like comparing different numeric classes as equal with a special equals method that just does that in particular. Some syntactic things. I've got a comma here in between the 2 key value pairs in this map. Commas are literally white space in Clojure. They read as white space by the reader. So that's there just because I thought it helped readability here. And then the colon things here are something you don't have in Java, which are, they're effectively interned names. And so we call those keywords. And the reason that we have them is that the interning means that we can do very fast equality checks. And it's sort of the canonical practice to use any sort of like domain entity like this. You're going to use a keyword as the key in your domain entity. And so they're used for map keys a lot. And there's actually special support built into the language for that. So domain objects. When we want to represent a domain object, we don't typically create a class or anything like that like we do in Java. We just create a map. And so we've got a map here with 3 attributes, first, last, and likes nachos. The values can be anything. It's all heterogeneous. The keywords are all keys generally. And this really constitutes this sort of generic data interface. We've got all of our domain objects have this same sort of structure to them with keyword keys. Because they're immutable, they're safe for concurrent use. You can pass around, do whatever you want with them. You don't need to copy them or do anything like that. Yeah.
Quick question.
Mm-hmm.
So the first, last, and likes nachos, would those be considered like elixir versions of atoms, where their value in the named value actually is the value for that type as well?
I don't know Elixir. So the panel says yes. So if we go back to our sort of touchstone example here, if you look at that one of those domain objects in Clojure, you'll see there's not like I'm actually using the tentacles library, which is a GitHub wrapper library. It's written in Clojure, and it just has this exactly what I would expect as a Clojure developer. So the keys are the attributes, and the values are the values of the attributes. And so it looks in some ways very similar to the JSON that we started with. There's not really anything between me and the data here. And you'll note that because every domain object's a map, every map has attributes. We've got a way to access attributes. That means that, like, if we think back to the thing where we have a repository and a user that have this HTML URL attribute from them, we can just generically ask for that attribute across any domain object that has it, and we can then retrieve that. And so that's where we start to get that. And there's lots and lots of built-in core functions that do things like give me all the keys, or give me all the values, or walk through a tree and increment a counter or something like that. There's lots of support for sort of generically navigating, retrieving, manipulating nested heterogeneous data. And so this is really well supported. And I don't think the Clojure Core API does everything, but it has the tools for you to build things too. So there are lots of utility libraries and people who've made things that go much further than what the Core API does. And that's possible to do because the tools are there to do it. I'm not going to talk about this in too much detail, or really just a slide, but Clojure has support for protocols and multimethods, which are ways to attach conditional behavior to data. So just like you would use an interface that has many implementations of a method. You have the ability to do the same thing in Clojure with protocols. So you can create a protocol and then extend that protocol to different types. And so it's really works well with typed data, typed maps. I'm not going to really talk about it all, but there's a sort of a typed version of a map called a record. And it has the same interface as a map. It has the same generic data access patterns to it, but it has a type associated with it. And it really does map to a real Java class under the hood. And so protocols work well with types. They work well with anything that's coming from Java. And multi-methods are really value-based conditional behavior. And so they let you say, given a piece of data, here's an arbitrary function that will produce a value that I can dispatch over. And so it's very powerful. You can take basically any of your attributes on the method call, compute anything from that, and then use that to switch on. So it's a different set of functionality. They overlap in terms of being able to support type-based things. You can do type-based dispatch with multi-methods too, but it's generally not going to be as fast. The key thing here, though, that I wanted to say is that these are both open systems. The behavior of both is open to extension to types added after the fact. So I can come along later and extend protocols or multi-methods to new types that didn't exist before. And that includes, like, protocols can be extended to final Java classes. So I can add new behavior to, like, string, for example. Sorry. So this is sort of getting into the how do I create abstractions and things like that. We also have separation of state and identity. So in Java, both identity and state rest in the object. The thing we have that we pass around is the thing that's mutable. And in Clojure, those two things are pulled apart. So every stateful construct that we create, and there's several different kinds of them, atoms and references and things, they have some current value. And we have a succession model where we'll get to the next value by applying a function. And so you don't say, set the value to this, you say, apply the function to your current value. And that's different. It allows you to then apply a function to the current state. And that means that you don't have to get the thing and then set it back, which creates that sort of need for coordination, basically. And so, like, the way we think about that is we might have an identity, some sort of stateful construct that represents today, and yesterday it represented that value November 7th or whatever. And you're going to apply a function which is add a day, and then today you've got a different day, and tomorrow we're going to apply the function again, and tomorrow you're going to have a different value. So you have the succession of values that transition through a pure function from one state to the next. Sequences. So sequences are logical lists, and so when you print them out, they look like lists, and you can sort of use them like lists. The API for a sequence is very simple. You can access it by first and rest with the two functions. So first is going to give you back the first element in the sequence, and rest is going to give you back a new sequence that represents the rest of the input. All the Clojure collections and lots of other things are seekable, so things that can produce a sequence. Unlike iterators, sequences are immutable, and that means you can safely pass them around between threads and give them to other people, and that you can diverge in sort of how you use them at that point. So, you know, you might have a sequence and you give it to another thread, and he starts iterating through it, which is fine. And then later on, I'm going to start iterating through it, and that's fine. You're going to be looking at the same exact data, and that's all thread safe. There's no issues with any of that. Because we just have this sort of API where we only need to be able to access the first element at a time, that means that we don't actually need to have the data. So if you get a sequence off of a view, you're actually sort of off of a collection, you basically have a view down to the underlying collection. And you're sort of eventually going to traverse the whole collection. But you can also create a sequence, a lazy sequence from a function. So you can have a function that produces a new value sort of as needed, on demand. And so there's lots of functions that do this kind of thing, like give me a range of numbers starting at 1 and going to whatever. Because you don't have to have the whole thing in hand at any given time, sequences can be infinite as well. And that's a common thing in Clojure. Like a really common thing is to say, like say I've got a list of keys and I want to initialize a map with a default value. It's really common to zip together a finite list of keys and an infinite initialization value. So you can create an infinite sequence of zeros and zip that together with a finite sequence of keys. So that's a really common kind of thing to do. So getting back to our example a little bit, this is an implementation in Clojure. So this most commits per repo is sort of the top level function. Here we're going to call org repos to give me back all of the repos in an organization. We're going to call map. Map is a sequence function that takes a transformation function and something seekable and produces a new sequence. So here we're taking a sequence of repositories, which are maps, Clojure maps, and we're going to map :name over it. And so :name, I said before, was a keyword. Here it's actually being used as a function. And so one thing that keywords do is they actually implement the function interface. And so if you pass an associative collection to a keyword, it will look itself up in the collection. And so this is a really common way to sort of do sort of generically, here I've got all repositories, but you see that this could be any kind of, the collection of any kind of objects. As long as they have a name attribute, it's going to give me all the names out. Yeah.
Is that a language level feature that's built into Clojure, or is that?
The name part, the keyword function part is built into the language. Map is part of the core library, and so it's just a function. So they're both kind of built in at different levels. Map name over repos gives me back all the repo names. And then I'm then going to map again over the repo names and say, give me back, call this most commits function. And here, this is actually an anonymous function syntax, this sharp blah, blah, blah. It's going to just invoke that function there on every name and repo names and replace the %. And so there's a bunch of different variants of this. And then at the end, I'm going to zip those two things together. I've got all the repo names, I've got all the max users per repo, and you just zip those together into a map, and so the result is a map. Does that make sense? Is there any questions on that? Yeah.
Could you go over the line of source of users, basically what is the most commits function doing?
We'll see that in the next slide, if that's your question. So most commits. You're my straight man, I guess. So most commits, here if given an organization and a repo and some credentials, we're going to effectively start from, let's see, can I get my cursor? I can. So here we're going to call into the library to go make an API call to get us all the commits in this repository. And then there's a lot of stuff packed into this one line here. And I would say that I fought with the stream stuff for a long time to make this fit, and it was not easy. So here we're going to start with, we've got basically a sequence of commit objects, and they're maps, sequence of commit maps. And we're going to call group by. Group by says, given this thing, apply this function, which we haven't seen yet, apply this function and group together anything that emits the same value. So anytime we see commits by the same author, that's going to be we're going to get out of this a map from author to a list of commits that returned that author. So this is a pretty powerful function, and it's only, like the implementation of it is only a few lines of code. I could probably actually show you that. Except I can't see. So you can actually, I don't know, I'm not sure what namespace I'm in here. So if you go look at the source for this function, you'll see that it's not that hard to actually write this function. There's a lot of optimization stuff in here that you can ignore, but it's really just walking through and doing a reduce. So that's not a very difficult function to write, but it's really, really useful. It's one that we use a lot for this kind of stuff. And then I'm going to sort by, so I've got this map. I'm going to sort that map by, so every entry is, the key here is author, and the value is a list of commits. So I'm going to take the value of that, which is the list of commits. I'm going to take the count of that, which is the count of how many commits were there. And then I'm going to sort by that value, the overall map by that comparator, right? So this is defining a comparator for us. And then I'm going to take the last one. So the last one is the one that had the most commits. You could flip this and sort it. It didn't really matter. This seemed to be the easiest way to do it. And what I'm going to get out of that is the last entry. And the thing I want out of that is the key. And so that allows me to pretty succinctly sort of find this answer and figure it out. The one function that I didn't define there was author. This is that logic that I had in the other one about looking up the user, the author, and all that stuff. Here I'm using this function called getIn. GetIn is one of our sort of deep traversal sort of functions that allows us to say, in this commit, look up the author key, and then take its value and look up the login key in that. And then, so this one's, so if I have an author, then I'm going to go look up its login. If I don't have an author, then I'm going to go look up the commit's author's name. So it lets me walk down pretty deeply into that nested tree. Yep.
Just a quick question, does the sort function get called for every comparison, or is it analog?
Does it get memoized? It doesn't get memoized. He asked, does the sort function get called, basically how is the sort function called?
Is it called for every comparison?
I believe so. Yeah, I don't think it gets memoized in any way. I mean, the problem with memoization is that when do you stop, right? So if you call this on a on a collection of a million things, that might be too many, right? It is possible to do that though. So there is a memoize function that you can use to memoize something, and you could apply that to this comparator function here and get that if you wanted it. So the tools are there to do that, but it doesn't do that by default, as far as I remember. Is there a question? Looked at that. So I want to talk a little bit more about sequence operations. What time is it? Oh wow, we're running late. Here I've got input, defining input as a range. This is it'll be all the numbers from 0 to 99. So this is an open-ended range call with a maximum on it. We can then map the increment function over that, and we'll get back 1 through 100. Example of filter. Filter will apply a predicate and give you back a sequence of all the things that pass the predicate. And then you can combine those together with something like filter odd map inc input. Clojure also has this alternate syntax that lets you use what's called the thread last operator here to take these two last expressions are identical in terms of what they do. There's just different ways to write it. And so the second one allows us to write it sort of in the order it happens instead of in this nested order. And people use both. It just kind of depends on context which one you want to use. But you're saying input, and then I'm going to map increment over it, then I'm going to filter odd over that. So just giving a little flavor for how those kind of things look. This is another example. If we have ground as a predicate, say this is a set of products that have some shipping data with them and weights and things, and I want to get the ground shipping weight, the weight of all the products that can be shipped by ground. And I want the total of that. So this is like maybe inside an order or something like that. So here I can take my products, I can filter out just the ones that are ground products. I can then map the weight out of them and then reduce plus over them. So I'm going to sort of reduce a collection down to a single number with a function. So this kind of stuff is just sort of bread and butter Clojure. But if we think a little bit more about sort of what's happening in that example, here we have the top thing is our initial objects that we've got, and I've colored the ground ones green, and then the weight is the number. So we're going to start actually with, say, a vector, and we're going to produce a sequence out of the top of that, and that's actually creating new objects over the top of that as your sort of immutable view. We're then going to filter out, I want just the green ones, or just the ground ones. So we create a new sequence. And then we're going to map the weight out, and I'm going to go from an object to just a number. That's, again, a new sequence. And then I'm going to reduce that to a single number. So this is sort of how Clojure is going to process those kinds of things. And I think when I see this, the question I ask is, well, what is that costing me to do all of that, all those intermediate steps there? And there is a cost. And I'm glossing over important details here that make this less of an issue, but there are things where data is chunked, 32 elements at a time, and that both helps in processing, it helps in sort of the inlining process, it also helps to reduce the object overhead, and then we also use what are called transients, which if you go down inside of a little particular method, you can say, turn on mutability, do some stuff really fast, and then turn it off again. And so that's also utilized inside of all this to help with both time and space. But there are some downsides to this sequence approach, is that It's lazy, but you don't always want it to be lazy. Sometimes you've got an external I/O resource, an API or whatever, and I don't want to lazily consume that over an arbitrary amount of time. I want to consume it now and have the data. And so that's a case where lazy sequences aren't great. We've got all this overhead, single-threaded. We can remove those intermediate sequences. This would be a way to rewrite this to remove that. So this is now an eager solution without intermediate sequences, but it's, I would argue, uglier. It's certainly, the pieces are not reusable in the way that they were before, and it's still single-threaded. We haven't actually solved that problem. So the idea with reducers, which was introduced a couple years ago, is that essentially all sequence operations can be implemented with reduce, sort of pass through where we're accumulating a value of some kind and passing through this state through the transformation. But we want to retain the sequence call model. We want it to look like we're doing sequence calls. And we want it to execute eagerly. And we want it to be automatically parallelizable. So as Rich has said, the future belongs to code that can automatically take advantage of more cores. And that's something that we want. So the way this looks is you use a different library which has many of the same kinds of functions in it. You make calls that are very similar. And the difference here is that when you call filter on products, it doesn't actually make the data at that point. It doesn't give you a lazy sequence. It doesn't do anything. All it does is it's sort of combining together the input collection and the reducing function. And every time you call one of these things, it just sort of makes a more complicated reducing function. And the input data is just passed along happily until the very end, at which point you call something like reduce or into or fold. And these things all will basically, at that point, execute the transformation in a single pass over the input data with a ever more complicated reduce function, and then give you back the actual answer. And the benefit here is that fold actually knows how to do work in parallel. So if you look at this actual process, if you go back to this slide, you'll note that like filtering out just the ground things or mapping, just pulling the weight out, like those things there's no order constraints there, right? They're just totally parallelizable pieces of work. And so fold can take advantage of this and actually uses fork join under the hood, Clojure's fork join, to build sort of a tree-like structure that first partitions your input data into hundreds of elements, chunks, reduces over each of the chunks, and then combines those chunks back together. Was it Christian? And so that's what reducers do, and they're really useful for that sort of thing. When I've got a lot of small pieces of data and I want to do parallel work on those things. And it's the same kind of thing that's happening in Java parallel streams. It's the same exact kind of an idea. They're using the same techniques with fork join under the hood. There really is a lot of overlap there. After that, so we've implemented these things like map and filter and stuff in sequences. Then we implemented them again in reducers. And then we wrote core async. And then we had these channels of values that were coming through. And then we needed to implement map and filter and all that stuff again over channels. And this is Rich Hickey's actual reaction when you do something 3 times. It's like, at some point you're like, maybe I should not have to re-implement these functions every single time in every single context, right? I should be able to, like what does map actually do? Like a sequence map iterates over each input element, it applies the mapping transformation, it appends that transform value to the output collection. So if you look at the implementation, you see all those pieces of it. But what is it actually about? It's actually about applying the map transformation. It's not about the iterating the input or appending the output. Those are separate. Those things are different in each of these contexts, but the thing that's the same is applying the map transformation. And so the question here was, how can we take that sort of notion and build something that abstracts the core of the transformation from where we get the inputs from and where the outputs go to? And that's what transducers are, which we're editing in Clojure 1.7. So transducers separate this essence. And just like reducers do, they They pull apart these different pieces and allow you to assemble sort of a recipe for a transformation that you can then compose the recipe without actually performing the transformation. It goes one step further than reduce. The reduce actually sort of keeps the source collection around. And so the calling model is a little bit different because transducers actually also abstract you from the source input. So transducers are eager, which have the benefit of sort of allowing you to control resource scope. They avoid these intermediate values, and they can be applied in many contexts, which can be pretty useful. You make them just basically by using the same sequence functions we already have, but you omit the input. So when you say things like map inc or filter odd, those give you back transducers. You can combine them with comp. It's just function composition. There's nothing like map inc and filter odd, just return you some functions that have a very specific shape. So there's nothing magical about it. You can go look at them, and they're easy to make. They're not hard to make to write your own. And so that's the thing you can do. If you go look at reducers, they are hard to make. I don't know that I would want to do that. They're pretty tricky, but transducers are comparatively easy. So we can apply those. In a case like this, we can say, build me a ground weight transducer that filters for ground and then maps for weight. And then I can call transduce to apply that transformation. Products at the end is our input elements. We then apply that transducing function, and then we have to say what to do with the outputs. And so that's what the plus is doing. It says, when you get the outputs, just add them together and start that adding process with 0. And so that's all that's saying. So we can do this in other ways. We can apply that to products. And then here we're not reducing to a number. We're just going to get back another collection. We can transform channels sort of asynchronously as they flow through these queue-like things. That's really it that I wanted to talk about. These are sort of the things we talked about. We've talked about 4 different models of transformation. That's all I have. So, any questions? Yeah. Hold on one second. No.
So when you get back a collection of things, if you didn't want to add them together, what would you put there instead of the plus sign?
So one thing you could do would be to, you could use, there's a generic function called conj, which stands for conjoin, and that's basically append to something. And so conj actually conges into a vector by default. So when you go back to something like this, instead of plus there, you could put conj. And instead of 0, you could put an empty vector or a list or whatever. Yeah, and that's exactly what N2 does. So that is how you implement M2. It does exactly that. Yeah. Any question? All right. Well, if anybody has questions about Clojure or anything, feel free to grab me throughout the day. Thanks.